Algebra 2, Section 3.2, solving systems algebraically. In particular, we'll be solving systems using elimination and substitution. Substitution first, actually, elimination a little bit later. This is something that has been covered in your Algebra 1 class over a chapter. We're just kind of condensing that down into one lesson or a couple of lessons. I think a chapter covered everything that we're covering in about 3 lessons here, actually. So elimination and substitution are getting covered in the same section because they're both algebraic. Basically, when they say substitution, what you need is you need to have a variable by itself, okay? So this one actually isn't the greatest example for substitution, but with one quick algebraic manipulation, we will be able to use substitution. So basically what we need to do is take this first equation here and subtract 3y from both sides. It's not the only thing that you could do, but it's certainly the easiest thing to do to get a variable by itself, meaning x equals or y equals. And we'll go ahead and do that. So really my system then is going to be x equals negative 3y plus 12, right? If I just took this equation right here and subtracted 3y from both sides. And then the second one can remain the same, negative 2x plus 4y equals 9. And using substitution basically works like this. Since you know that x equals this right here, since you know that, you can substitute it in for x right there. That's why it's called substitution. Now, when that happens, you're going to have negative 2. You're multiplying it by the quantity, so put it in parentheses, the quantity, negative 3y plus 12, and then it's plus 4y equals 9. In effect, what you've done is you've eliminated the variable x, so now you have this equation that just has a y in it, which you can solve. Now, I use the word eliminated, and actually elimination is the other algebraic method for solving systems, so please don't confuse that. But in fact, in either case, what you've done is you've eliminated a variable. Okay, so this is substitution because of the step right here, but now we can solve this because there's only y. So let me just quickly do that. I'll distribute the negative 2. This will be 6y minus 24 plus 4y equals 9. Go ahead and add 24 to both sides. At the same time, you can combine like terms with the 6y and the 4y. I said add 24, so that's going to be 33, and then divide by 10, and you'll get y is equal to 3.3. Okay. Well, now what do? Remember in the 3.1 lesson that we learned that a solution to a system is an ordered pair. So we need x comma y ordered pair. And the truth is you could plug this y anywhere you want up here. Okay. Now I think that you should use this one since it's already solved for x. I think that's the easiest one. So we'll do x is equal to negative 3 times 3.3 plus 12. And negative 3 times 3.3 is negative 9.9. Plus 12 would be 2.1. X is equal to 2.1 when y is equal to 3.3. The last thing you ought to do is put them into an ordered pair like this. Okay, and then just one other thing, if you want to check it, of course you can. If you want to check it, I wouldn't check it into the equation that you just plugged in. I would check it into the other one. So you could go negative 2 times 2.1 plus 4 times 3.3. And yes, we're wondering if that's equal to 9. Okay, and it will be. And you can check that if you want to. It's going to be 9, so it checks. Okay, moving on to the next one then. At Rinaldi's Pizza, a soda and 2 slices of pizza of the day cost $10.25. A soda and 4 slices of pizza a day cost $18.75. Find the cost of each item. Now we can write these equations. We could just take the situation and write the equation. 1 soda plus 2 slices of pizza, so I think 1s plus 2p for pizza, equals $10.25. 1 soda and 4 slices of pizza, 1s plus 4p, equals $18.75. They probably have that written here already. Yeah, there we go. Okay. Now again, this would actually be very conducive to elimination as well. But they're asking us to use substitution, or they're kind of building upon the concept from the last example of substitution. So what you'll see them do next is solve for s on one of those. Okay. They took the first equation, subtracted 2p from both sides. That's how you get this. Okay. That's in red. And then they're going to substitute that's in red in for s right here. Okay, now you just saw me do that once, so you probably don't need to see me go through the motions again. Do note that if this were a minus sign, you would be subtracting the quantity 10.25 minus 2p. Since it's plus, it doesn't matter, but just note that it's the whole quantity, 10.25 minus 2p, that's getting plugged in there. And there's their work, and they solved, and they got p as 4.25. That means that a slice of pizza is $4.25. Then they take that p and they plug it back into one of the equations, doesn't matter which one, and they find that s is equal to 1.75. So again, a slice of pizza is $4.25. A soda is $1.75. Okay, moving on. This says use the elimination method. Now this is where you have to have things in columns. You got to have the x's in the same column and the y's in the same column, and basically the equal signs need to be top over bottom from each other, and the constants the same. Usually, almost always when we see an elimination problem, it's in standard form, as these two equations are both in standard form. And I'll tell you what, I always wondered, when I was your age, I wondered why this works. Why is it that we can just add down in columns and it works? Let me give you a quick explanation as to why. You see, this right here, this negative 3x minus 2y, we're being told that that's equal to 12. These are two quantities that are equal, okay? So if I take this and I add it to this side of this equation, and I take what it's equal to, 12, and I add it to the other side of the equation, essentially I'm adding the same thing to both sides of the equation, like you're allowed to do. That's the addition property of equality. So I'm adding the left side and adding the right side. It just is helpful and convenient to have the x's here, the y's here, the equals together, and the constants. So I'm basically adding down. And 3x minus 3x plus negative 3x would be 0. This has to happen. You have to have a variable get eliminated. This is why it's called elimination. When I add down here, y plus negative 2y would be negative y. Negative 9 plus 12 would be negative 3. Okay? And I'm sorry, positive 3. Yeah. Not negative 3. Positive 3. Negative 9 plus 12 is positive 3. But the y itself is negative, so when I make it positive, y is going to become negative 3. The y value is negative 3. If negative y equals 3, then y equals negative 3. Okay, so if y equals negative 3, then we can plug that back in again. You can pick either one. I've already modeled this for you once, and I'm trying to keep the video short, so I'll just show you their work. It's going to come out to negative 2. You plug negative 3 here and solve for x, you'll find that x is negative 2. Or if you plug it in here, you're going to find that it's negative 2. The solution, x equals negative 2, the solution is negative 2 comma negative 3, the ordered pair. And there's their work if you want to see it. Negative 2, negative 3. All right, let's keep going. Here we have one that they say solve by elimination. And you should notice that, again, you have standard form, and they got the m's over the top of each other. We got the n's, we got equals, we got constants. It feels like we're good to go, but there's a problem. The problem is if I add down here, 2m plus 3m is 5m. 4n plus 5n is 9n. You're just going to have a new equation here that says 5m plus 9n equals negative 7. And while that statement is true, that sentence actually is true, that equation, that's not helpful. We haven't eliminated a variable. Now we just have another two variable equation. So we want to do something to these two equations, one or both. In this case, it's going to be both, so that we can make it basically to have the same number top over bottom, but different by a sign. One of them is positive, one of them is negative. So for example, if I multiply this top equation through by 3 and this bottom equation through by negative 2, I'll have 6m plus 12n equals negative 12, multiplying every term by 3, and then negative 6m minus 10n equals positive 6. Now, as an alternative, you could have also multiplied the top one by 5 and the bottom one by negative 4. Then you'd be eliminating the n's instead of the m's. You could have also put the negative here instead of the other. I mean, there are some options here. You also could multiply through by positive numbers and subtract down, but I will never model that for you because I see too many students make mistakes subtracting. I will always do the multiplication to get the numbers the same and different by a sign. So it's like 6 and negative 6, like you see here, because the subtraction has just been a disaster whenever I see students try it. So I'd encourage you to do what I just did there. And now we'll add down and we'll get that 0. get 0 right here. Add down here, 12n plus negative 10n is 2n. Add down here, we're going to get negative 6. And then when I divide by negative 2 to get n by itself, I'm going to have n is equal to negative 3. Okay. Now, once again, I could plug this negative 3 in really for any place, any of these four, to solve for m. And I'm just going to show you what the answer is because I want to move on. It's 4. M would be equal to 4. And of course, if you use the top equation here to plug n in to get the m equals 4, then I would take the other equation and type 3, or write 3 times 4 plus 5 times negative 3 and see if it's actually equal to negative 3. Use one equation to find the second variable. Use the other one if you're going to check. Okay. Now, as far as ordered pairs go, if you're going to give it to me as an ordered pair, and by the way, when it's weird variables like this, you can certainly just give me that. Okay. But if you're going to give me an ordered pair, you got to do alphabetical. 4, negative 3. M comes before n in the alphabet, so it's 4, negative 3. Or just to be safe, you could also do this. M, n equals 4, negative 3. Okay. Almost done. One more. That's one more example, two extra situations actually. Notice, and we've done enough work, I think, so notice what they're going to do here. They're going to use elimination by first multiplying through and then adding down. And when they add down here, notice negative 6x plus 6x is 0, 10y plus negative 10y is 0, 12 plus 0 is 12. Now, how often is 0 equal to 12? The answer to that would be never. 0 is never equal to 12. This is where we say no solution. So you're working it out just as you're just thinking it's a normal problem. You work it out and you end up eliminating all the variables, not just one of the variables, but both of them. And you get a false statement. 0 equals 12. 0 is never equal to 12. So this is going to be a no solution situation. Incidentally, if you graphed them, these would be parallel. They would not be intersecting. When there's no solution, they have no intersection. This is the situation. So graphically, these are parallel lines. Algebraically, you get the false statement, 0 equals 12, or negative 3 equals negative 18, that kind of thing. Okay, that's not ever going to be true. So we say no solution. And then lastly, kind of the other exception to just getting a solution is you're working it out and you get a true statement. 0 equals 0. How often does 0 equal 0? 100% of the time. Well, in that case, what we're going to want you to say is infinitely many solution. Now, I do know that the book does something a little bit different with this, and I'm not a fan of it. So just say infinitely many solutions. I'll show you what they do. We're going to say infinitely many solutions. And again, graphically, you might wonder, what does that look like? Because they're lines after all. Well, what that would look like is a one line graphed right on top of the other. I don't know what this line looks like necessarily, but if I graphed the line and it looked like this, and then I graph the other line, you'd graph it right on top of the first one. They're actually the same line. They're the same equation, just a different form of the same equation. Okay, so that's the infinitely many solutions. It's not all solutions. Don't say all, right? If it's two lines and we draw them and they happen to be the same line, is this a solution over here? Is this point here a solution? No, only the points on the line are the solution. So with that, and that's why they kind of do this, even though I'm not a fan of it, this is why they do what they do. They're just going to give you what the solution is all the solutions to this equation. This would be the slope-intercept version of these two equations. These two are the same equation, just different forms in standard form. One's a multiplier of the other. And then this would be what it is in slope-intercept form. I'm not a fan of that. Let's just stick with infinitely many solutions. All right, thanks for tuning in.